In Chapter 5, we're going to start looking at probability distributions. For 5.1, we will just be looking at basic probability distributions. Your learning outcomes here is going to be to distinguish between discrete and continuous random variables, construct and read a probability distribution in its graph, determine if a distribution is a valid probability distribution, and calculate the mean, standard deviation, and variance of a discrete probability distribution. Once this section is complete, for each scenario you would be able to state the type of study that's best, give the variable that is being measured, and classify the variables as discrete or continuous. So B and C are things that will be new from 5.1, and you guys should already be able to read these different examples and state the study. Each example on the previous slide involves random variables. So a random variable is a single numerical value that is determined by chance or has a random element. We usually use X or Y or Z to represent random variables. Variable in this class does not mean an unknown algebra answer. It means outcomes of a single trial of a probability experiment. Some examples of random variables: the number of miles one tire lasts before it wears out, the number of accidents at an intersection on one Saturday. X could be the amount of time running a 5K for a single client. We have the number of puppies in a single litter, number of sales calls a salesperson makes in one day. Another example is time spent on sales calls in one day. So these are all random variables. A probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or a graph. Discrete random variables have a collection of values that is finite or countable, so we can list these without skipping. Continuous random variable has infinitely many values, and the collection of values is not countable, so we cannot list without skipping. I really want you to visualize what is happening here. So a discrete random variable is something where we can easily count, like the number of accidents, things like that. Continuous random variable, I want you to think about it as if I have two students' heights and one is taller than the other, then can I find another student that would fall in between the first two students' heights? And we would be able to. But then if you break it down even further, could I find two students then to go in between each pair of other students? So what I'm looking at here, just kind of so you can, I want you to kind of visualize it. If I have a person, I can find someone to go in here, right, that is falling between the heights of the first two people. But then I should also be able to find more students that can go in between them, and you keep going and keep going. So a height is a continuous random variable because you can always find something to go in between. Time is also continuous because you're breaking down as far as even milliseconds. So what is discrete or continuous? The number of miles one tire lasts before it wears out. Since we're talking about a number of miles and that is a distance, this would be continuous. The number of accidents at an intersection on one Saturday, that would be discrete because we would be counting the number of accidents. The amount of time running a 5K for a single client will be continuous because you're always going to be able to find someone else's time that falls between two others. The number of puppies in a single litter would be discrete because we can just count how many puppies were born. The number of sales calls a salesperson makes in one day, you're counting the number of calls, so that's discrete. The time spent on the sales calls in one day would be continuous, again, because we're working with time. So there are requirements to be a probability distribution, and to be a probability distribution, it must satisfy each of the following 3 requirements. 1, there is a numerical random variable, so it cannot be categorical, it must be numerical. 2, the sum of the probabilities must equal 1. And 3, each individual probability value must be between 0 and 1. Here, let's look at an example of a coin toss. So we're going to consider tossing 2 coins and let X be the number of heads when 2 coins are tossed. The above X is a random variable because its numerical values depend on chance. All of the possible outcomes that we could have here, we could have a heads, tails, a tails, heads, a heads, heads, and a tails, tails. So how many values can X be? Remember, we are looking at the number of heads when 2 coins are tossed. So we can get no heads, 1 head, or 2 heads. So we have 3 different values. And here you can see that I have already written those values down for you in this number of heads column. So again, we could have 0 heads, 1 heads, or 2 heads. Now, to find the probability, then you're just going to look at that, all those possible outcomes, and determine what the probability is. So the probability of getting 0 heads, that means we're getting a tails, tails, is 1/4. Okay? So I'm going to just come over here, 0.25. How many times do we only see 1 heads? Well, we see that twice by heads, tails, or getting a tails, heads. So that's 2/4, or 0.5. And then we could get heads twice with heads, heads, which is 1/4, or 0.25. So if we look at this, our first requirement, so just back to those requirements, there is a numerical random variable. We already said counting the number of heads is numerical. The second requirement is that the sum of the probabilities equals 1. So if we add up our probabilities here, so 0.25 plus 0.5 plus 0.25, we should get a sum of 1, and that is correct. And that third requirement is that each individual probability is between 0 and 1, and we can see that here. They are all between 0 and 1. A probability histogram is similar to a relative frequency histogram, but the vertical scale shows probabilities instead of relative frequencies based on actual sample results. And you can see here, this vertical scale, or our y-axis, has probabilities instead. So this is the probability histogram for the number of heads when 2 coins are tossed. Here we have an example with job interview mistakes. Hiring managers were asked to identify the biggest mistakes that job applicants make during an interview, and the table below is based on their responses. And this is based on data from an actual survey. Does the table below describe a probability distribution? So here we're looking at it. We have X is inappropriate attire, being late, lack of eye contact, checking on the phone or texting. We have the probabilities, and we also have the sum of all the probabilities. So the table violates the first requirement because X is not a numerical random variable. The values are categorical, not numerical. The table also violates the second requirement because the sum of the probabilities is 1.57, and it should be 1. Even though the probabilities are between 0 and 1, those other 2 things are not true, so it cannot be described as a probability distribution. Let's look at an example of constructing a probability distribution. An owner of a mid-sized company wants to measure the morale of her employees and gave a survey. One question was, how satisfied are you with your supervisor? Responses varied between 1 as being very dissatisfied and 5 very satisfied. The table below summarizes the results. So we have our responses of 1 to 5 and how many times she saw those answers. We are going to first convert the frequencies to probabilities. So we have how many total surveys. So the sum here should be 200. And then you're going to convert these frequencies to probabilities. So the probability she got a 1 is 27 over 200. So 0.135. The probability of getting a 2, 16 out of 200, 0.08. The probability of getting a 3 is 52 out of 200, which is 0.26. The probability of getting a 4 is 44 out of 200, which is 0.22. And the probability of getting a 5 was 61 out of 200, and that's 0.305. So all I did was take the frequency, divide it by the total number of survey results she had, and simplified to a decimal answer. So our question now is this a valid probability distribution? The first thing is, are the X values numbers? Yes, the responses were 1 to 5. Is each probability valid? So that means, is it between 0 and 1? And if we look at those probabilities, yes, it is between 0 and 1. And do the probabilities add up to 1? So if you add up, we should get 1. So yes, this is a valid probability distribution. You can use those probabilities and create a probability histogram. You may want to go ahead and pause this video here and go check out the Constructing a Probability Distribution in Excel video that I have created. We are now going to look at the parameters of a discrete probability distribution. So to find the mean, we will do the sum of all the x's times the probabilities. The variance is going to be the sum of all the x minus the mean squared times the probabilities. And then for the standard deviation, we'll just take the square root of the variance. We will do these calculations in Excel, and I am going to go through them in a video, so you can either look at the next couple slides as I just quickly talk through it, but I'm going to have a more detailed video for you to watch as well. So to find the mean in Excel, you will have a column for your x values, a column for the probabilities, and then you're going to make a column so that you can multiply each x by its probability and then find the sum of that column. Here you can see the general look of what this should look like. This is using the satisfaction score and those probabilities from the earlier example. And if you do that, the mean of this distribution is 3.48. To find the variance and standard deviation in Excel, you will have your x columns, your probabilities, and you are going to need to know the mean. Then you're going to need to have a column subtracting the mean from each x value. And then you're going to need to do a squaring column for the values from step 3. And then you'll need to do a multiplying the values from step 4 by the probabilities. Find the sum of the values in step 5. That would be your variance, and then take the square root of the variance to find the standard deviation. Again, I have a video you can watch that's more detailed and showing you step by step with me talking through it. And it will be called Finding Variance and Standard Deviation in Excel. Here is what it would look like. So I have my x scores, my probabilities, and then I have a column here with my x times my probabilities with the sum, and remember that value is my mean. And now I can keep going to find that variance. So you have to remember what the formula is, right? So it's the sum of x minus mu squared times p of x. So what you're trying to do first is this most inside part, x minus mu. And that's what we're doing in this column. And then you're going to square here. And then you multiply by the probabilities. That sum is your variance, and then you square root that to get your standard deviation. If you would like to see the step-by-step video for finding means, variance, and standard deviation in Excel, you can pause the video here and then come back once you watch my Excel video. When we are looking at the mean, we need to be able to interpret what it's saying. So the value of mu will rarely be an actual x value, and that's okay. You don't have to make it a whole number. We interpret it as a typical or expected result of the probability experiment. So for tossing coins, mu is 1. We generally expect to get one head on 2 consecutive tosses on average. For the satisfaction survey, our mean was 3.48. So that means we generally expect employees to be neutral or somewhat satisfied on average. We will be looking at significant values again when we are looking at probabilities. So remember that significantly low is less than 2 standard deviations below the mean. Significantly high is more than 2 standard deviations above the mean. And anything falling within 2 standard deviations is not significant. Significantly high number of successes. X successes in N trials is significantly high if the probability of X or more successes is 0.05 or less. So that means that the probability of X or more is less than or equal to 0.05. The value 0.05 is not absolutely rigid. Other values such as 0.01 could be used to distinguish between results that are significant and those that are not significant. So significantly low numbers is going to be that the number of successes if the probability of X or fewer successes is 0.05 or less. So that means X is significantly low if the probability of X or fewer is less than or equal to 0.05. Again, 0.05 is not a rigid value. That's just what we're looking at right here. So let's look at finding an expected value. At a raffle, 1,500 tickets are sold at $2 each for 4 prizes. We have a $500 prize, a $250 prize, a $150 prize, and a $75 prize. You buy 1 ticket. What is the expected value of your gain? So what do we mean by gain? Gain would be whatever you win or lose. So let's look at how we find this expected value on the next slide. So to find the gain for each prize, you need to subtract the price of the ticket from the prize. So your gain for a $500 prize, okay, so remember you're winning $500, but you had to pay $2 for the ticket, so that's $498. So if you win the $250, again, you're subtracting your ticket price, that is $248. If you win the $150 and subtract your ticket price, it's $148. And the $75 is $73. So if you do not win a prize, okay, so you do not win a $0 minus 2, that is -2. So these are all of your possibilities here. Expected value of a discrete random variable is equal to the mean of the random variable. So this is very important that you remember it. The expected value of a discrete random variable is equal to the mean of the random variable. So remember, the mean is the sum of all the x times p of x. So that means the expected value of a random variable is a weighted average of the outcomes. Likely outcomes get more weight than unlikely outcomes. So the probability distribution for the possible gains, or those outcomes, one person is going to win the $500, so that's that 498 gain. One person for the 250, and so on. But you see, then everyone else, okay, that's where this number is coming from, everyone else is going to lose. So the expected value is going to be the sum of all the x times the p of x. So you're going to need to do each individual one. So multiply x times p of x at each one of these. Okay, so I've got 498 times 1 over 1500 plus 248 times 1 over 1500 plus 148 times 1 over 1500 plus 73 times 1 over 1500 plus that negative 2 times 1496 over 1500. And then when you do the sum of all of those, you get negative $1.35. So what does this mean? It means you can expect to lose an average of $1.35 for each ticket you buy. To practice this section, you will want to check out your MyStatLab homework 5.1 and your lab manual pages 42 to 44. And if you have any questions, of course, go into Microsoft Teams under the Unit 2 questions and post there.